All right, 4.2 is a section on inflection points. Now, we started looking at local maxes and local mins, and those were all related to the first derivative. Inflection points are something that we're going to use with the second derivative. So, by definition, an inflection point, which you'll often see notated as IP, okay, inflection point is the point on a graph where it changes concavity. Okay, so we've talked a little bit about concavity before, but just as a reminder, a graph that is concave up looks like a cup. Concave up. And where it's down, we call it concave down. Okay, we've also talked about how the sign of the second derivative is related to the shape of the graph. So when it was concave up, the second derivative was positive, and when it's concave down, that second derivative was negative. Okay? When we talked about this before, we said that when we talked about second derivatives, it could be concave up, concave down, or neither. Okay? An inflection point is sort of a special neither. So the inflection point is where it changes concavity. So what does that look like? Could look like this, okay, right here. This point, if you look to the left, it's concave up. So here the second derivative is positive. To the right, it's concave down. Second derivative is negative. Similarly, the shape could have been more like this. Inflection point's right about here. Again, negative here, second derivative, positive here. But it's this exact point where we change, okay, concavity. And as you can see, if the second derivative is greater than 0 here and less than 0 here, as you can imagine, this point where we change concavity is exactly where the second derivative equals 0. Okay? So an inflection point has the property that at an inflection point, that second derivative equals 0 right there. Now, you need to be forewarned, this does not work in the other direction. If you find that the second derivative equals 0 somewhere, that does not necessarily mean it's an inflection point. It could be, but it might not be. However, if you have an inflection point, then the second derivative is 0. So it only works in one direction. Okay? So remembering that's the point where it changes concavity, okay, we'll want to make sure that when we find inflection points that it is actually an inflection point and not sort of what I call a trick spot. Okay, so let's look at an example of how we find these and how we calculate them, because as you know, we like to work with functions with numbers to find interesting places. So let's say we have the function x cubed minus 6x squared plus 4x plus 9. Okay, so we have this function here, and we want to find the inflection points of this function. Okay, well, we know that inflection points happen when the second derivative equals 0. So our first hunch here is to find the second derivative of this function and find where it equals 0. So to find the second derivative, we need to first find the first derivative. So again, here we have basic polynomial. So here the 3 comes down out front. Subtract 1 from the power. So we have 3x squared minus, now the 2 will come down to multiply the 6, giving me 12x to the first power. Remember, subtract 1. Plus the derivative of 4x, when you just have a constant times x, the derivative is just that constant. Then the derivative of 9, when you have just a constant, the derivative is 0. So now, we take the derivative of that function to find our second derivative. So the derivative of 3x squared, the 2 comes down to multiply the 3, giving me 6x to the first power, minus the derivative of 12x is just 12. Okay, so my second derivative function looks like this, 6x minus 12. To find the inflection points, I want to know when does this equal 0? Okay, because we know that if there's an inflection point there, the second derivative will equal 0 at that point. So I add 12 to both sides. 6x equals 12. Divide both sides by 6. And I get x equals 2. So x equals 2 is my candidate. Okay, I'm thinking it's probably an inflection point, but I need to make sure. There's two ways. You can always graph this function on your calculator. If you plug it in, you look at x equals 2, you'll be able to see if it's in the inflection point. However, we can also do this mathematically. Okay? Well, how do we do it mathematically? We know that we want it to change concavity to the left of the point and to the right of the point. So what we'll want to do is pick an x value to the left and to the right of our inflection point and see if the second derivative changes sign when we plug those numbers in. So something to the left of 2 would be 1, to the right would be 3. Okay, so we want to check the sign to the left and to the right. So when we plug in a 1 here, 6 times 1 is 6, minus 12. Okay, 6 minus 12, it's a smaller number minus a bigger number, so it's going to be negative. So the sign to the left is negative. Okay, to the right, we're going to pick a number to the right, like 3. When you plug in a 3 here, 6 times 3 is 18. 18 minus 12 is positive 6. Okay, so as long as you change signs from the left to the right of your inflection point, then we changed concavity, so it is indeed an inflection point. Okay, it doesn't matter if it changes from negative to positive or positive to negative, as long as it changes. Okay, so now we've ensured that's an inflection point, and we can answer the question, this function has an inflection point when x equals 2. Okay, let's quickly look at one that has sort of a trick inflection point. All right, so let's say we have the function f of x equals x to the 4th. Okay, so we want to find the second derivative. So we start with the first derivative. So here the 4 comes down, x, we subtract 1 from the power, giving us 4x cubed. And our second derivative, okay, the 3 will come down to multiply the 4, giving you 12x squared. So we ask the question, when does this equal 0? That'll give us our prospective inflection points. So this is going to be 0 only when x equals 0. That's the only thing that'll make this second derivative 0. Okay. So x equals 0 is our possible inflection point. Okay. So we want to check something again to the left and to the right to make sure that we actually change signs, because if the second derivative changes signs, that means we changed concavity. So we can check x equals -1, that's a little bit to the left of 0, and x equals +1, that's a little bit to the right. When I plug in a -1 here, -1 squared times 12 is +12, so it's positive to the left. And then when I plug in 1, 1 squared times 12 is also 12, so it's also positive. So here, unfortunately, we did not change signs. We went from positive to positive when we checked to the left and to the right, which means it's not an inflection point. Just like if it had gone from negative to negative, if it does not change, it's not an inflection point. Okay, so it's a trick. So here, if I asked you to find the inflection points, the answer would be there are no inflection points. And if you were to graph this, okay, to check what's going on, you would see that this graph of x to the 4th is sort of like a parabola, but it comes down, sort of flattens out, and comes back up, okay? So here it's just a weird flat spot, which makes the first derivative 0, which makes the second derivative 0, and it's not actually an inflection point. Okay, so just be careful of that and make sure that you check all your inflection points to make sure that they are indeed inflection points. Okay, so let's try some examples and we'll pair this up with the maxes and mins and sort of look at the whole picture.